Alright, welcome to another AQA chemistry video, and today I'm going to be doing a video on electron shells, subshells, orbitals, and electron configuration. So, the electronic structure, the placement of electrons in atoms is complex, and there are several levels of organization. So this is the atom, this is a phosphorus atom, as you know it from GCSE. So you have your energy levels, which is the electron shells from each, from the intersection. Know the energy level. You know the electrons are arranged in electron shells. So you have a first energy level. The first shell will be the first energy level. The second shell will be the second energy level, and the third one will be the third energy level. And electrons can be excited up an energy level. As per the Bohr model, electrons are arranged in shells. So Niels Bohr model, which is the one you do at GCSE, and I understand at GCSE, and well, you have to you understand electrons a bit differently when I'll explain it later. But the shells are defined by the principal quantum number and given by the number n. So principal quantum number n, that should represent your shell, right? The lowest energy level has n equals 1, and n equals 2 will be the next one, and so on and so on. Other shells have higher energy and higher n. So the first energy level, or the quantum number 1, that would have the lowest energy, and that's because the electrons are closest to the nucleus, and so they're very strongly attracted to that nucleus, and they wouldn't move as much. Whereas electrons which are on a higher energy level, so n equals 3 for example, they're further away from the nucleus, so they feel that positive attraction less, and therefore they're more free to move a bit more. They're still in place, but they move a bit more freely compared to, and therefore they have more kinetic energy compared to electrons in the first shell. So the higher the n of an electron, the further away from the nucleus. So yeah, the higher the n of an electron, then the further away from the nucleus it orbits. Subshells. For atoms with more than one electron, shells are split into subshells that have slightly different energies. The difference in energy between the subshells is much less than the difference in energy between shells. So you have your subshells here, right? For example, like you have little subshells within the shell, and the energy difference between the shells, the energy difference between subshells is much less than the difference between whole shells. And that's what I'm just getting about here. A shell with a given n will have the same. So a shell with a given n will have n subshells. So for example, if it's n equals 3, if the third shell will have 3 subshells, and I'll show them to you later. So orbitals. Subshells are composed of orbitals, and orbitals in the same subshell have the same energy. Each orbital can hold a maximum of 2 electrons. So these subshells will have, so as I said before, so a shell of a given number n will have n subshells, and these subshells, if the subshell is in, so orbitals in the same subshell all have the same energy because they're all the same distance from the nucleus. You know, they're the same equidistant from the nucleus, so they have the same energy. But and each orbital have 2 electrons. I'm going to go through the type of orbitals that you would get, or type of subshells that you get within each shell, and the type of orbitals that you have. And to summarize, electrons occupy orbitals. An orbital can hold a maximum of 2 electrons. A set of orbitals of the same energy is called a subshell. Subshells make up different shells of electrons, and different subshells don't have the same energy. So I say, if I was to focus more on orbitals, the concept of an orbital is key to understanding many chemical properties, and one orbital can only contain up to 2 electrons. The types of orbitals now. So orbitals are labeled by letters. There's the first 3 orbitals are called S, P, and D. There is another one called F, but you rarely ever have to use that in the exam, but there's technically 4, but the ones you'll use mostly are S, P, and D. And S subshells. So this is the part. This is the difference between A level and GCSE electrons, because this is much different compared to what we understand from GCSE. GCSE needs to know 288, and it's just not like that in reality. It's not like that. They run it in orbitals, and I'll show you how they are actually done. So it's an S subshell can have 1 S orbital. A P subshell is made up of 3 P orbitals, and a D subshell is made up of 5 D orbitals. And orbitals of exactly the same energy are called degenerate. So if I was to show you the box method for this, you'd have I'll put it down here. S orbitals, you can represent them within the box diagrams as well. And if you're having 1 electron, that's just, you have to do this, and an electron is a half arrow. And for 3 p orbitals, you have, so for p orbitals, you have 3 of them. Oh. Right, well, this is not working with me. You fill them, when you fill up your p orbitals, you actually fill them in with half arrows, the first orbital first. So you do it like this. That's how you actually do it. And then you would then complete it in this way. So if it has 5 electrons, it would look like this. It wouldn't look like 1, 2, 3, 4, and then, well, I guess actually that's probably not a good example, but actually I could probably get rid of this. If it was 4, it wouldn't be 1, 2, 3, 4, and then leave it there be. You fill up the first orbital, the first electron fills each orbital first. So 1, 2, 3, and then 4. And that'll be for P. And then for D orbitals, that's 5. It's the same concept, but it's just with 5. And now there are some instances where you need to do oh, actually, that's wrong. I shouldn't have done it like that. You do each one first. There are some instances where you don't follow the rule. Like, if you had something like this, it's better to have a partially filled. There might be some instances where you have to get a partially filled D subshell, and it doesn't like to do like that, so you wouldn't really leave it like this. This is more unstable. It would probably be you'd have 1 less orbital. So there are some exceptions to the rule. Shells and subshells. So n equals 1 is for the first shell here. You only have the s orbital, and it'll just be 1 s2. It's a subshell with just an s subshell, and then we have n equals 2 shells. It has 3 subshells, and there's an s and a p subshell. I'll probably explain this better when you see it again. I'll come back to it so it makes more sense. But n equals 3 shells has 3 subshells, an s, a p, and a d orbital. And a d subshell. When you're filling the orbitals are filled from the lowest energy to the highest energy. And the usual energy order is from S to P to D to F. Usually is going from low energy, so S to P to D to F is like the highest energy level. But there are some exceptions to this, because transition metals are the anomaly, where the 4s subshell is of lower energy level than the 3d subshell. And so the filling order is 3s, 3p, 4s, and 3d. This is all going to be very confusing to you at first, but there is a way that my teacher always taught me. Shout out Miss Dr. Bakari and Miss Doyle. I'll shout them out. But more importantly, there's just a simple way of memorizing this, and you should do this in the exam in case you forget. So, electron shells, just to sum this up. You have either n equals 1, which is just 1. To summarize for electron shells, in the first energy level, there's only one, there's only an s subshell, where there's only one 1s orbital. In the second energy level, there's an s subshell and a p subshell, where there's only one 2s orbital and 3 2p orbitals, as I showed before. Remember I said there's only one s orbital, one s orbital, and then we have your 3p orbitals in the subshell. In a p subshell, when it's maximally full, it will have 3p orbitals, and then if your 3s orbitals in your third energy level, you have an s subshell, a p subshell, and a d subshell, which will contain, when it's maximally full, it will have one 3s orbital, 3p orbitals, and 5 3d orbitals in that subshell. So D subshell would have 5 3d orbitals. Now we're going to get down to electronic configuration. The electronic configuration for is made up of 3 parts: the principal quantum number, the subshell, the electron occupancy of that subshell, and the shells. And most importantly, the shells are populated from the lowest energy to the highest energy. All this means, all of this can be defined in one thing, right? And this is what I was trying to say before, with what you need to draw down in your exam. This is how I remember it, and this is the easiest way to remember in what order in what order the electrons come from, and how to know which energy form, how it goes from low energy to high energy. So the lowest energy orbital will be 1s, and you write in a grid like this, right? 1s, and you go, let's just go down to 5, right? Let's go down to 5. It can go lower, but let's just go down for 5 for the sake of it, right? 1s, you write in a row: 1s, 2s, 3s, 4s. Let's say you have 5 energy levels, right? The first shell is only gonna have a 1s only. The second energy level is gonna have a 2s and a 2p. The third energy level is gonna have a 3s, a 3p, and a 3d orbital. And 4s, you can see the pattern going here, having a 4p, a 4d, and a 4f. Same principle applies here: 5p, 5d, and a 5f, and there's only f is the maximum. But if you want to understand how they go in order, if you want to know the electronic configuration in which order, the best way is done like this. You do downwards arrows in this direction, and it's actually perfectly the order that they go with. And if you want to go lower, obviously it can apply to going over. For the sake of this here, it would run like this. So if someone asked me, right, the electronic configuration of lithium, which has 3 electrons, so I know it has a 1s2 and then a 2s1. But let's go for something that has a bit more, let's go for something that has 20 electrons, right? 20 electrons, I don't know which atom in the periodic table has that, but I'll probably try and find one here, but let's get our periodic table out. 20 electrons. Calcium. I think this is the right example. So if I was to do calcium following this way, this always comes up in the exam. Always comes up in the exam. They ask you, what's the write down the full electronic configuration. It's alright. 1s2, the number of electrons goes as a power. 1s2, 2s2, 2, it's not in frame, sorry. 1s2, 2s2, 2p6, 3s2, that's 10 already, so that's 12, 3s2, 3p6, that's 18, and it's not 3D, the next one here is 4s2, and that's 20, and that's how it would go down. So, because someone that may not understand, they would just go straight across and go straight to, yeah, they just go straight to 4s instead of going to, so they go from 3p and they go to 3D. I nearly confused myself there. You go to 3p and then they go straight to 3D when instead it should be going to 4s. And then if you were to go again, you would go to, then you'd go to 3D if you wanted to, if there's more electrons. And if let's see, let's go on a bit more. Let's go and say 3d6, right? If I wanted to have 26 electrons, it'd be 3d6. You jump back up here again, and then down to 4s. Or if I complete this to be 3d10, and then 4p2, and so on and so on. But that's how it's meant to be done. And that's it. Hopefully this video helped. I know I stutter a lot, but I try.